Okay, I'm still there. I have to go to autocatalytic reactions. So we go now to autocatalytic reaction. So it's a reaction in which one of the products of reaction acts as a catalyst. So take note that one of the products of reaction acts as a catalyst. So in this case, the product of reaction R is the same time acting as a catalyst. So the more R you have, the faster your action would be. So you have here also R and another R in here, because this product is also achieving the purpose of a catalyst, that is increasing the rate of reaction. Now, if this is the way we write our autocatalytic reaction in which one of the products of reaction is acting as a catalyst, I'll go back to the unprojected slide because it cannot be projected properly. Go back here. So you have it here. The rate would be then K, C sub A, C sub R, because we have these two species on the left side of your chemical reaction. The rate of A, or the rate of reaction of A, is K, C sub A, C sub R. Now, the total number of moles of A and R, in this case, remains unchanged as A is consumed, yielding the relationship that at any particular time, so at any particular time, the sum of the concentration, of your product acting as a catalyst and your species, reacting species, or your reactant would be the same. So initial concentration of the two is equal to the sum of their concentration at any particular time. Why? Because it's a constant. The sum of the two concentration is a constant. Now, if that is the case, so I'd like to go back here. You could see that you have C sub R in here. And we have to change the C sub R into an expression in terms of A. That way it would be able, or we could be able to process this differential equation that we have, if we will not consider that the C sub R is totally a constant in itself. And where we're going to get that particular equation that will help us change the C sub R here in terms of C sub A. We will get it here. So your C sub R would be equal to CaO plus CrO, which could be CO minus the C sub A. So that's the expression that you're going to see here. So the CO is the sum of the initial concentrations of A and R, and of course, you have C sub A in here. So you could see now that the C sub R expression was changed to this. Now, your DE for this matter now has your unknown function as C sub A and your independent variable as time. So you can process it again using separation of variables and method of partial fractions. If you use the method of partial fractions, so breaking into partial fractions, this will be the corresponding expression that you will be getting. Okay, you have either the ln of CaO times the quantity CO minus Ca divided by Ca times the quantity CO minus CaO. Or it could be something like this, which is to be equated to COKT, where C sub O is the sum of the concentration of CaO and CrO. KT was just copied in here. Now M can replace the ratio of CrO to CaO, just like M is representing CbO over CaO with respect to second order and third order irreversible reactions in the beginning part of this set of slides. So now, from this expression, you will have this for your autocatalytic reaction. So you have now the M and the conversion in this side equated to this. So CaO and M again. So if you notice in this side, you have this as a constant. The M is a constant in itself. The rate constant is also a constant. So the only variable here is T. The only variable here is XA. If the problem provides you with initial, or rather with concentration of A, you can always change this XA to an expression coming from Ca being equal to CaO times the quantity 1 minus Xa. So there's no problem with this limiting you. because you can always get an expression of XA in terms of C sub A, if it's C sub A that is provided in the problem. Now, what are the things that we are to take note of when we speak of autocatalytic reactions? So when we speak of autocatalytic reactions, it's a requirement class that some product R must be initially present if the reaction is to proceed at all. So meaning if no amount of R is initially present, the reaction will not happen. Unlike the homogeneous catalyzed reaction that even if we don't have the presence of the catalyst, the reaction would still proceed. This one, it's a requirement that you have some product R initially present. Now, the rate will increase as more R is formed. This is, I think, very self-explanatory. Since R in itself is acting as a catalyst, the more R you are producing, the faster the reaction would be because the catalyst hastens the reaction. When A is about to be used up, or that is when it's totally consumed, or we can say that you have more or less reached 100% conversion, or you are nearing 100% conversion of A, the rate will drop to 0. I think it's again self-explanatory. Why will the rate drop to 0? Because there's no more R to form, because your A is about to be fully converted to R. So in that case, when A is about to be used up, nothing left of it, the rate will drop to 0. When is rate maximum in the case of autocatalytic reactions? So rate is maximum when the concentration of A and R are equal. So when the concentration of A left and when the concentration of product R are equal, then the rate is maximum for the said autocatalytic reaction. Now, a plot of time and concentration for autocatalytic reaction yields a straight line passing through the origin. Why is he saying that it will yield a straight line passing through the origin? If you notice, there's no y-intercept here in this particular equation. So then we don't have a y-intercept. So if there's no y-intercept, then your line is to pass through the origin. Okay? So that's in the case of our autocatalytic reactions. Okay, we have an example here. I place it here because we don't have a sample, I think, in Levenspiel that will have autocatalytic reaction principle illustrated or is to be applied. Okay, we have this sample problem. The reaction below is elementary, and the product R has a catalytic effect. So I chose this example because it's not limiting us only to a scenario wherein you have a single reacting species here on the left side. So this time we have 2. Plus, the products on the other side are also 2. Plus, this R has a catalytic effect. So this is an autocatalytic reaction. So the data that's provided here is that we started with the same initial concentration of A and B, and that's 2 moles per liter. And of course, it's a requirement, we just read it a while ago, that our R should be initially present, or some R should be initially present for the reaction to proceed at all. So initial concentration of product R is 0.1 mole per liter. So it was observed that with this particular scenario, after 10 minutes, 40% of A is converted to R and S. Find the specific reaction rate, the concentration of A at which the reaction velocity is maximum, and the time when the reaction velocity is maximum. Actually, letters B and C are connected. So the concentration of A at which reaction velocity is maximum, and when is this, or what is the time when reaction velocity is maximum. But before we can answer B and C, we have to answer letter A, and that's the specific reaction rate. Okay, so we will now process this problem. So we'll go back to our whiteboard. Okay. To write down the given. A plus B forming R plus S. So your R has a catalytic effect. Then we have initial concentration of A and B being 2 moles per liter. And after 10 minutes, A is 40% converted. Now, our initial concentration for R is 0.10 mole per liter. And we have 3 unknowns. So for letter A, we have the specific reaction rate. That would be the K. Letter B, concentration at which A reaction velocity is maximum. So we say C sub A when rate is maximum. So we want the concentration of A when rate is maximum. And here T when rate is maximum. Okay, these are our information in the problem. So now we go to the next. I'll just change this one. We have the solution. Now, if we go back to this one, it's unlike the first one that we have originally derived because the species here are 2, and like the example wherein we only have 1 species. So you have to write your own rate expression. So we go back to this slide here. We have the rate in terms of A will be equal to, can somebody give me the expression for the rate in the case wherein we have 2 species here on the left side? How would we write the rate? Anyone? Autocatalytic reaction. The rate would be, okay, I'll write here dCA dt first. Kindly provide me with the rate law here on the right side. How would I write the rate law on the right side? Would it be the rate constant times the concentration of A times the concentration of B times the concentration of R? Why is this missed? Why you have included that? Because if we have an autocatalytic reaction, remember, you have A plus B. But your R has some catalytic effect. So you have to write R here. And you will have your R as S plus another R. Just like the way we do it with homogeneous catalyzed reactions. So it's the same thing here with autocatalytic reaction. So now, since you have the presence of the R on the left side of your chemical reaction, you have to write the corresponding concentration in the rate law already. Okay, so that would be now your rate expression. So we have a problem if this is the case. So negative dCA dt, because we want to deal with this differential equation, there has to be a way of, I'd like to change again. There has to be a way of changing C sub B in terms of A and changing C sub R in terms of A. Because if this original expression we retain, or we don't change the C sub B and C sub R in terms of C sub A, we cannot evaluate the DE, because the DE dictates that you should only have one unknown function. So anybody here who can suggest me on what to do with these two concentrations? We can start with something simple, like an expression for C sub B. Then we go to the expression in terms of C sub R, because these two has to be changed. It has to be changed in terms of C sub A. So I'd like to write here C sub A, and I'll be waiting for C sub B and C sub R expressed in terms of C sub A. What do you think, or how should we do it? Class, how should we do it? Any suggestion? Okay, you started with the same initial concentrations for A and B. So these two are equal. And we know that CaO times 1 minus Xa is Ca. Now, next is we have Cb. We like to have Cb because this Cb has to be changed. So, just like this one, we write CbO 1 minus Xb. So, I'll wait for, I'm giving you already the starting point. What do you do next? I have already CbO times the quantity 1 minus Xb. What do you think would be the next thing that we do? We can have CbO minus CbO XB. It's still Cb. Then, what about this? Isn't this CaO also? The CbO that I wrote here is also CaO. What about CbO-XB? In relation to CaO-XA. In here, in your stoichiometry, the amount of A reacting is equal to the amount of B reacting. Why is that? Because they have the same stoichiometric coefficient in your chemical reaction. So this now, the CbO-XB can be changed to CaO-XA, Cb. What is this? Isn't this one? Class, are you still there? Are you with me? This CaO minus CaO-XA, which I placed here for CbO minus CbO-XB, is actually this one. So therefore, C sub A is equal to C sub B. Oh, C sub B. This one, C sub B. So your C sub B is equal to C sub A. So I will write here another C sub A. That's for the C sub B. So C sub B and C sub A are just the same. So next is C sub R. Where do we get C sub R? Let's say I'll keep this question mark here. I'll go back to that later. So this is equation 1. Where do I get C sub R? You can always go back to this, like this one.
Sa CO minus
Sa?
CO equals C sub A plus C sub R.
You have CO is equal to
C sub A plus C sub R.
C sub O should be C sub AO, C sub BO plus C sub RO. Is this what you mean? Which is
Miss.
also equal to CA plus CB plus CC, right? Autocatalytic
Yes,
reaction.
Miss.
Okay. So then we have something to use now. So where is the C sub R here? You are right. This is correct. But where is C sub R in that particular equation? This is a correct relationship. It's one of the principles of autocatalytic reaction. The thing is, however, we're trying to find a replacement for C sub R. And it doesn't have C sub R. So I need an equation that has the presence of C sub R. Where do you think should we get it? We can start with this one. Nothing goes wrong with this relationship, but I would only equate C sub R and C sub A, okay? So I will place here C sub AO XA over R is equal to CRO XR over 1. CAO XA over 1 is equal to CRO XR over 1. The CAO XA, you know, I'll go here na lang. Next slide. Or here. So you will have continuity. So we have this now being equal to CRO XR. This represents the amount of A reacting. This represents the amount of R formed. So take note, the amount of R formed. For the amount of A reacting, this would be what? Isn't this C sub A minus, or C sub AO minus C sub A? Do you get this? Why? Because of this class. CA is equal to CAO times 1 minus XA. And this is CAO minus CAO XA. I want this. Then this transferred here would be CAO minus CA, right? Now, can you give me an expression for CROXR? The amount of R formed is what? Since R is being formed, it's a product. So we have here C sub R is the initial amount times 1 plus XR. Now, a good opportunity to show to you why plus, because R is being produced. You don't consume R, so it should be plus. It should not be minus. So you have CRO plus CRO XR. Then you can get now this one. Your CRO XR is concentration of R at any time minus the initial concentration. Okay, somebody is chatting. CRO plus, so it should be minus, okay? CR minus C sub O, C sub RO. And we want, remember, we want an expression for C sub R. So C sub R then must be equal to CAO plus CRO minus CA. The problem gives us that we're starting with 2 moles of A and CRO is 0.10 minus CA. So C sub R then must be 2.10 minus C sub A. So you substitute 2 to 1. You go back here, this one. So this would be now your C sub R. The C sub R would be now 2.10 minus C sub A. So I have this. So what would it look like now? So it would be something like this. Wait. Okay, so it would be negative dCA dt equal to K. Now, I have a CA there, you recall? This one, so that would be CA squared. So that would be CA squared. It should be multiplied to 2.10 minus C sub A. And the rest will be your math. Okay? You use your calculator because anyway, we have the limits. If we don't have the limits, you use the method of partial fractions. So CA squared, this separation of variables here, transferred here, and we have K dt. This side will have to start with an initial concentration of A, which is 2. We started with 2, and a final concentration of, what do you think is the final concentration, by the way? So again, we'll put here a question mark. This would be 0 to what time? So we're given what? And go back to the given so you will recall what to apply. What information here will you use? In the given, that way we can find the CA and the time. Third year, are you still there?
10
What?
minutes to
Okay, 10 minutes and the conversion. Okay, that was, I think that was Joshua. So we go here. So we'll place here at t equal to 10 minutes, XA is equal to 0.4. So CA can be solved from here. CAO, 1 minus XA. So you have a 2 times 1 minus 0.4. This must be a 0.6, so this is 1.2 mole per liter. Then this must be 10. And still, and this must be 1.2. Okay? So if you process this in your calculator, since you're dealing with a definite integral, you can find the value of the K. So I will wait for that value of the K. So this is your integral here. These are your limits. So you will have a value here. And this side, you will have K times 10. So you'll be able to get the value of the K. Can you please solve for it? Your answer here should be 0.0773. This is a third order reaction. So this must be a liter per mole squared per, what's the time here? Minute. Okay, so that would be the unit of the K. Please check if you're able to get that one so we can proceed with the next two requirements. Did you get it?
Yes, miss.
Okay, so I will proceed now. So that was our letter A. This is our letter A. Any questions so far here? Okay, we go to B. So B is asking for the concentration of A when rate is maximum. Concentration of A when rate is maximum. What concept have you learned in the past when you use here? Concentration of A when rate is maximum. I'll give you an
CA equals CR means.
CA is equal
Are you
to
sure?
rate.
CR.
Rate is maximum when the concentration of A and R are equal. Correct. Correct na siya. So place here R sub A is maximum when C sub A and C sub R are equal. However, we don't know the time when they will be equal because it's being asked in letter C. Good if we know the two already. Okay, I'll write here a clue so you'll be guided. So let's say if I write my rate expression or my rate law. So that would be this. And what was the value of the R? 0.0773. So this is 0.0773 CA squared 2.1 minus CA. So there is it. There it is rather. I've written the rate law to give you a clue on how to find the concentration of A when rate is maximum. You will learn, you have learned already the tool in the past on how to get this maximum rate or the concentration when rate would be maximum. What is that particular tool?
If the derived means.
Correct, Joshua. Very good. Maxima and minima in your EMA 101. So you will differentiate this rate law. You'll get the derivative. We don't place here negative. You have to get the derivative of the rate with respect to CA. Just like this is Y and this is X. So if you get the derivative, that would be 0.0773, and you will use product rule. First term times the derivative of the second minus the second times the derivative of the first. And maxima dictates that this should be 0, maxima minima. If this is 0 and you have this constant, automatically that constant will also be out of the picture. So you have the 0 being equal to negative C sub A squared minus, so if we would distribute, this would be minus 4.2 C sub A plus 2 C sub A squared. This is 4.2, right, minus. This one is plus, correct. So you have now 0 is equal to C sub A squared minus 4.2 CA, or 0 is equal to Ca minus 4.2. So concentration is 4.2 moles per liter when rate is maximum. Okay? Do you get it? Okay, silence means yes, no question. We go to the next. So last question. If you, what was asked? What was asked, by the way? You are asked T when rate is maximum. Or what will you do? The time when rate is maximum. Anyone? Time when rate is maximum. We have dCA, dt. Okay, somebody wrote in the chat box. Let's see. Substitute CA. Substitute CA where? Where will you substitute CA? Rate law. Okay, you cannot substitute in the rate law, Iho, because if you will substitute in the rate law, you won't be able to get time. You mean in the rate equation. Is that what you mean, Jobern? You substitute CA in the rate equation. So you will set up your integral again like this. And you will have 0.0773 dt. Yes, I'm sure yes. Rate equation, correct. Sa rate equation, very good. So you will place here, starting with an initial concentration of 2 and a concentration at the maximum rate, which is 4.2. That's your final here. And you have here 0 to t. So you will have t as the remaining unknown. Okay, so you process this side, you will have a value here. Then your right side would be 0.0773 t. You'll be able to get the t. Your t would be around 8.07 minutes. Please check. Did you get it? Did you get it? Yes. Okay, so I think silence is a yes. So process this one. You should be getting 8.07 minutes for the time when rate is maximum. Okay? So I will transfer now to our slides. It's almost time. I will end with the, I'm done with the autocatalytic reaction, and we're here on the irreversible reactions. There's plenty of things. There's a lot of things to do. Okay, cannot project everything, so we'll have it here. Hi, so we'll end with this, but we cannot end with a sample on this because it's almost time. But I'd like to discuss this in a manner that you can follow easily, okay? Irreversible reactions in series. So in series, we will limit only our irreversible reactions in series here in a two-step series reaction. So we won't anymore have another branch here or another step here. So something only comparable to this, okay? If we will start with only A, meaning there's no R and there's no S initially present, now we will have this rate of reaction in terms of A, on the consumption of A. So that's K1CA. You can follow that. If you will process it, you will have this answer. Excuse me. So CA transfers here. You have this answer for your DE. You simplify, you will have this. So it enables you to solve for the concentration of A at any particular time, as long as you are given the initial concentration and K sub 1, the rate constant of the first reaction or the first step in here. Okay, that's for C sub A. Now we go to the next. If we will set up the rate equation in terms of R, and R is being produced from the first reaction, so this R is a product of the first reaction, then we'll write it as positive. So dCr dt here is positive, and it's K1Ca. But R is also being consumed in the second step. So that would be K2C sub R, as you can see here. It's a minus because we have written the rate in terms of R considered as a product. Now, if you will transfer this C sub R here on the left side of the equation, you will have dCr dt plus K sub 2 C sub R being equal to K sub 1. And take note that the Ca was now replaced by the formula that we have derived here from the first step. Ca being equal to CaO e raised to negative K sub 1 T. Now, you have this. And this is the first time that you will encounter a differential equation in kinetics that now will be using linear DE. So if you recall your linear DE, if you're finding the, or if you're to evaluate the linear DE, you are to find the integrating factor. Okay, so you will need to review on how to find the integrating factor for the linear DE. If you know already how to find the integrating factor of the linear DE, the solution of the linear DE is dependent on that linear factor. Okay, but that would be something for you to review because you're done with it and I'm sure you can recall it easily. The corresponding formula yielded from this first order linear differential equation will be this one. A formula that solves for R, the intermediate, we call it intermediate, at any time as long as all the constants are known. What are these constants? What are these all constants that I'm referring to? The initial concentration of A and the two rate constants. Because your formula is just dependent on the three, nothing else. And of course, the time. So you can solve for the concentration of the intermediate at any particular time given this particular formula. So please review from linear DE and how you evaluate such or how do you find its solution. So that's it. Now, so far, we have a formula that allows us to solve for the concentration of A at any time, this one, and the concentration of R at any time, this one. So of course, the next is, the very important is, what's the concentration of the final product? Because this is the species that we are most interested in, the final product or the product. Now, how do we find S? S is being formed in the second step, and if it's a product, then its rate of formation is equal to K sub 2 C sub R. Now, noting that there is no change in the total number of moles, meaning whatever is initially present for A, that would be equal to the sum of what is present of A, R, and S at any particular time. Let me explain this. The initial concentration of A is equal to whatever is left of A plus whatever is formed of R and S, which was taken from A. Okay, I think this is very common sense. R and S came from A, and there's no amount of R and S initially present. So it follows then that the initial concentration should be equal to whatever is left of A, we're talking of A, plus the two substances that were formed from A. So you have C sub R plus C sub S in here. Now, what's the purpose of this? If you have already a formula for Ca and you have a formula for C sub R and you know the initial concentration, it would be a simple case of subtracting these two expressions, this formula and this formula from CaO, and you will have C sub S. And this is it. The formula that allows you to solve for the final product at any particular time. A formula that is only dependent again on the rate constants of the two steps and the initial concentration. Now, what are things that we can deduce or generalize from the derived formulas that we got from our two-step irreversible reaction in series? These are the generalization. If K2 is much larger than K1, K2 is the second step, right? So if K2 is much larger than K1, the final amount of S formed will be only dependent on the first step. The amount of S formed will only be dependent on the first step. Rate is determined by K sub 1, the first step of the two-step reaction. Otherwise, if K sub 1 is much larger than K sub 2, meaning K sub 1 is faster or the first step is faster than the second, just like in here, the second is faster than the first, then the formula for solving for the final concentration of the product will be dependent only on the second step. So reaction is governed by K2, the slower of the two-step reaction. In here, we go back to the very fundamental concept we've learned in Chemistry 1, that the rate of reaction is dependent on the slowest step, which we call the rate determining step. So since K2 is larger here, the concentration of the final product is dependent on the slowest step, which is, of course, the first step. Since K1 here is larger, then K2 must be slower than K1, then our final concentration for S will be dependent on this particular step. So anchored upon that fundamental principle of the rate determining step, or the slowest portion of your, or the slowest, shall I say, step in your series of reactions. Now, the time when R concentration is maximum, this is pre-derived for you already, but you can make an exercise out of this. How do you determine the time when the intermediate concentration is maximum? It's equal to this formula. It's the reciprocal of the log mean of the rate constants. The time when the intermediate concentration is maximum. Now, what is this maximum concentration of the intermediate? It could be solved using this ratio, or simply transfer CaO here, and you have again a formula that is dependent on the rate constants. Okay? The time when the intermediate is maximum, the concentration of the intermediate when it is maximum. Now we go to the generalization. In a two-step irreversible reaction in series, we have observed that A decreases exponentially based on the first step. R rises to a maximum. We expect that R is going to reach a certain maximum value, but then we expect it also to fall because it is also being continually consumed or used up in the production of S. So of the three species, it's S that is rising continuously. The greatest increase in S, meaning the greatest rate in the formation of S, is observed when R is maximum. I think this is very self-explanatory. If there's a lot of R to be used up in forming S, then of course, the greatest increase in the rate of production of S will be based on that maximum concentration of R. K1 and K2 can be evaluated by noting the maximum concentration of the intermediate and the time when this two concentration is reached. This bullet here that I placed is referring to these two. If you intend to know K1 and K2, this has to be known and this has to be known together with the initial concentration. Why? You have two unknowns. Two equations, two unknowns will lead you to the unknown. So this is the thing that is being referred to in here. You solve the two equations simultaneously. And that ends about irreversible reactions in series. Last of the multiple reactions will be the reversible reactions class. So we'll end here for now because it's time already. I'll stop sharing. And since we still have a lot to cover, stop